Quantification theory part 2. In the last module, we looked at predicate calculus, right? So predicate calculus, I pointed out, well, in fact, it's an artificial linguistic system. It's not natural language. It's inspired by natural language, or by those parts of natural language that contain quantified statements, but it wasn't directly an analysis of the relevant expressions that you do find in natural language. Now, let's come back and take a look briefly at what you need to do if you wanted to use the insights that we gained from predicate calculus when we look at the semantics of a natural language that contains quantified expressions. Now, before we move on, let me briefly point out something. In predicate calculus, the expressions that are generated by the grammar of the predicate calculus, they don't contain ambiguities. In fact, there are certain kinds of ambiguities that you find in natural language do not in fact appear in first order. Let's give one example. In first order predicate logic, let's consider the two formulas. For all x1, there exists an x2 such that kx1, x2. Compare this with there exists an x2 such that for all x1, k1, x1, kx1, x2. You can show that these two statements are not logically equivalent. The second statement entails the first, but the first statement does not entail the second, which means that they are not synonymous. Now, and hence, these two simply, they simply have different truth conditions. Now consider the counterpart of statements like this in natural language. So let's look at the following statement of English. Suppose I say every man loves some woman. It seems that in English and many other natural languages differ a little bit about how much, not every natural language will give you examples of what I'm just about to tell you, but English certainly does. The English statement, every man loves some woman, can be understood in more than one way. One way of understanding this statement is to say that you pick all the men, each of the men loves some woman or the other. If a male person A loves a woman B, and a male person A prime loves a woman B prime, B and B prime may be distinct people. So it basically means something like every man loves some woman or other. But this statement can also be understood in a slightly different way. That is to say that there is a particular woman whom every man loves. Example, the person in question could, for example, be Hema Malini. So suppose we are in a universe where Hema Malini, the actress, is loved by every man. We could describe a situation like that by saying every man loves a woman. That woman is the man. Okay? Now, in English, this statement, every man loves a woman, seems to be ambiguous. It is. Now, where does the ambiguity come from? Remember, in both ways of understanding, it's clearly not a case of lexical ambiguity, right? Because in both senses of this sentence, every means the same thing. Man means the same thing. Loves means the same thing. Some means the same thing. Woman means the same thing. So this is not, there is no lexical ambiguity in this sentence. It also looks like there is no obvious syntactic ambiguity in this sentence, right? Because in both cases. Every man is the subject. Some woman is the direct object. Loves is a transitive verb. The transitive verb combines with the noun phrase to give you a verb phrase, which then combines with the subject to give you a sentence, and those relations are seen to be identical in the two senses of this sentence. If that's the case, what's going on? Now notice we can express the two senses of this statement in natural language by formula over predicate logic. In fact, the same formula over predicate logic that I have just mentioned previously. For all x1, there exists an x2, blah, blah, blah. There exists an x2 for all x1, kx1, x2. Now, the expressions of predicate logic are not ambiguous. You express the two senses by using two different formulas. Each of them is ambiguous. But the natural language expression seems to be ambiguous. Now, how do you deal with this kind of an ambiguity in sentences is often where that contains more than one quantified phrase is often called an example. These are taken to be examples of what we call scope ambiguity. Where do scope ambiguities come from? How do we deal with scope ambiguities in a theory of the syntax semantics? One of the things that happens is that VP ellipsis is a grammatical phenomenon. Grammatical phenomena are typically attuned to ambiguities, to genuine ambiguities. Okay? So suppose I say, I went to the bank and Bill went to. The second is understood as referring to a bank, okay? But the sense of bank in both the first form and the second form must be the same kind of. If you interpret bank to mean a place where you deposit money, then if I said John went to the bank and Bill did too, you mean Bill went to the place where you deposit money. It could not mean that John went to the place where you deposit money and Bill went to the place to say a riverbank or something. Now, sometimes in our use of language, we could play with such apparent violations, but we immediately recognize these to be a case of irony and so on. But as a grammatical phenomenon, normal, non-playful uses of language, you have to interpret the elided VP and the first VP in roughly the same way. What this means is that if there is a genuine ambiguity, VP ellipsis is a kind of phenomenon that is sensitive. Now consider the following example. Suppose I said a Canadian flag was flying. Let's take the following example. An American flag was flying in front of every building and a Canadian flag was too. Now consider the sentence. An American flag was flying in front of every building. This sentence can be understood in one of two ways. There is one Canadian flag that's flying in front of every building. Maybe the buildings are around in a circle or a semicircle, and there's a flag, there's an American flag that's flying in front of each of these. Or it could mean a different American flag flying in front of every building. So again, these are the two ways of understanding this sentence. Is this a case of genuine scope ambiguity or simply a case of us being vague about the set of circumstances that make this sentence true? Now, let's suppose we put this in an ellipsis context, and I tell you an American flag was flying in front of every building and a Canadian flag was too. There is something interesting that goes on. If you interpret the first sentence in one way, you have to understand the elided VP, you have to understand the second sentence plus the elided VP in exactly the same way. So if you take the first sentence to mean there's a different flag flying in front of every building, you have to interpret a Canadian flag also to mean a different Canadian flag in front of it. If you mean the same American flag, the second one also has to be interpreted as the same Canadian flag. Now, there are facts like these that argue in favor of viewing these two ways of understanding these examples as involving a genuine case of ambiguity. Now, if this is in fact a case of ambiguity, how does the theory of the syntax semantics math deal with this? Now, it's possible to have different approaches to this question. There is one approach that says, okay, we need a more complicated semantics than we have had so far. Okay? So we have a sentence, every man loves some woman. We all know what the syntactic structure is. We just complicate our semantics in such a way that we can get the two different readings of the sentence. There is another way of dealing. There's another approach to dealing with examples of this kind. And that is to say that despite appearances, these two, our semantics is in fact very simple. It's just like the semantics that we know for first order predicate logic. But contrary to appearances, we are dealing with two different levels of syntax. We are dealing with a level of syntax where in fact the syntactic structure corresponding to these two readings is in fact different. Now, clearly, this syntactic level cannot be the same as the surface syntactic structure, one where you have a subject, verb, object, verb, and object for the verb phrase, but rather you have to have a structure where your noun phrases can be moved around, leaving a gap. And this is a gap that's exactly like the kind of gap that you find all the time in natural language. In many languages, you form a question. So suppose I say, suppose you want to ask, suppose John bought a book. You don't know what John bought, and so you ask, what did John buy? You use a sentence where what is the direct object of the verb, but it's not, instead of being pronounced right next to the verb, it's pronounced at the beginning of the sentence. And instead of where you would expect the gap, where you would expect the direct object to be, you have a gap. Similarly, in relative clauses, the man who Mary met today, meet is a verb that normally takes a subject and an object, but in this case, who Mary met, who corresponds to the person Mary met. Okay? Instead of a direct object of the direct object of meet, you have a gap that corresponds to who. So we see that there are many structures in natural languages where you can argue that there are gaps left around. People who have argued in viewing the map from the syntax semantics in this way basically claim the following. Let us assume that the surface syntactic level is not the level where your semantic rules apply. Instead, you can have operations that move things, but move things in such a way that it doesn't affect the pronunciation of these sentences. Essentially, what you have is, and so what you get is you will get syntactic structures that look a lot like statements of first order predicate, like formulas of first order predicate. If you say something like, every man loves some woman, you say that some woman moves to the front of the sentence, leaving a gap. Every man moves from its subject position and adjoins to a sentence node, again leaving another gap. Whenever things they move, whenever constituents move, they leave a gap that's co-indexed with them. So if you index the noun phrase every man with the index 1, it will carry the index 1. The gap will also carry the index 1. If a woman carries the index 2, the gap it leaves will also carry the index 2. And you devise your semantic rules in such a way that they apply, instead of applying to your surface syntactic structures, they will apply to what are called the logical forms of these sentences. The term that we use in linguistics for these is the word logical form, uppercase L, uppercase N. Now, in linguistics, when we use the term logical form, we don't want to confuse it with the philosopher's sense, which is why we capitalize the L and the F when we talk about logical forms. Logical forms in linguistics are taken to be strictly, they're taken to be a level of syntactic representation to which rules of semantic interpretation apply. These are syntactic structures that are obtained from surface syntactic structures by moving things around covertly. Covertly because they don't affect the pronunciation of the sentence, but they make a difference to the semantic interpretation. So that's what we mean by logical form. Okay. Now, let's say we look at a fragment of natural language that deals with quantified statements. As before, let's look at this third fragment, call it F3. What would F3 look like? S goes to NP-VP, NP goes to N sub P, N sub P goes to Hema, Shahrukh, Raj, just like before. NP now can also go to det N sub C. Now we are bringing in common nouns. N sub C goes to man, woman, book, fish. S goes to neg S. S goes to S conj S. VP det goes to every some the. VP goes to VI, V sub I. VP goes to V sub T, NP. VP goes to V DT, NP, PP 2. V sub I goes to sings, dances. V sub T goes to likes, hates. V sub DT goes to gives. You can also add a few others, takes, and so on. So this is your basic phrase structure grammar that generates sentences that you need. You also have to have another rule, which is not a phrase structure rule, but it's a special kind of rule that we call the rule of quantifier raising. This is a rule that will take a noun phrase and move it from its place and adjoin it to a sentence node that dominates it. This can be formulated by saying, suppose you have a structure consisting of material X followed by a noun phrase followed by material Y. All of this is contained in a sentence. You can transform this into another structure where the noun phrase is moved and it forms part of a bigger sentence and is adjoined to it, and where the noun phrase used to be, you now have a gap. Okay, so you have an S that dominates an NP co-indexed with an I, followed by X, E sub I, where E sub I is a gap, followed by Y, E sub I, and NP I are co-indexed. So this allows you to give you structures of the following kinds. Okay. What does the semantics of statements like this look like? Now, you can find the details of the semantics when you read the module. Okay, I will very briefly go through it. Here's what the semantics of quantified statements looks like. Just as in the previous module, you need to interpret logical forms by means of what we call models. Models consist of basically ordered pairs consisting of U and V. U is a universe of discourse. V is a valuation function. V of neg is, you know. V of and, you already know. V of or, you already know. V of man is the set of all things that are men in our universe of discourse. Now, this is something you have to remember. I did get time to mention this, but remember, common nouns are predicates, just like intransitive verbs and verb phrases that we are familiar with. Now, you need to think a little bit about this. Consider common nouns like cat and dog. Okay, look at the arguments that we gave for predicates before. What are cats and what do the linguistic expressions cat and dog do? Cats are things that are cats. Cat is the common noun cat, doesn't denote an object, doesn't make it by itself, it can't make. It is not true or false. It divides up the universe into those things that are cats and those things that are not dogs. They have all the properties that Evans mentioned about predicates. In other words, you can just take them to be predicates. We know what predicates are. Okay, so V of man, V of woman, V of book are basically, you know. Similarly, V of sings, V of hates, you know what they are. V of loves and hates are two-place predicates. You already know what their semantic interpretation looks like. What's new here? Well, there are two things that are new here. You have variables that are new, and you have quantifiers that are new. Now, in order to interpret quantified statements, you need special kinds of rules. These are rules that you just see here. In order to interpret gaps that are left, we call these gaps traces in syntactic theory. These are simply interpreted as variables of first-order logic. How do you interpret these? Well, you just interpret them via assignment functions. In order to interpret these, your rules for quantification will be quite like the rules you had for quantification when we talked about predicate logic. So every time you interpret a quantified statement, you consider all those assignment functions that are exactly the same as the original assignment function you started with, but you're allowed to vary, to assign different values to a particular variable, and that, in fact, gives you the kind of semantics that you see there. Once the semantics is given, we can, just as with predicate logic, define entailment, contradiction, validity, and logical equivalence. Logical form, a sentence with the logical form entails another sentence with the logical form, if and only if every circumstance in which the first logical form is true, the second logical form also must be true. A sentence S with a logical form is a contradiction if and only if the logical form gets the value false in every possible circumstance. It's valid if it's true in every possible circumstance. Two logical forms are logically equivalent if and only if they get the same value in every circumstance. Okay? So once we have this, you can think of the semantics of quantified statements, assuming once you have your basis in predicate logic, you can simply extend this to a fragment of natural language that contains all of these quantified expressions.